So let me take a moment to summarize the story so far before we go on to the physical system of the mass on the spring. So we've been talking for quite a while about these special kinds of ODEs, second order linear homogeneous with constant coefficients. So it's something that has this kind of form. Oops. Yeah. Where A, B, and C are numbers. So A y double dot plus B y dot plus C y equals 0. A, B, and C are some numbers. If you have that kind of equation, you make this guess, y equals e to rt, plug it in, and you get an equation for r, which we call the characteristic equation. There's three cases here. So that's a quadratic equation. Your characteristic equation can have two real roots. So the solutions, you can have r1 and r2, which are real numbers. And then my solution will be y equals a e to the r1 times t plus b e to the r2 times t, and this is a smooth function. There's no oscillations here. You could have the characteristic equation which has one root which is repeated twice, and then we talked about how to solve the equation in that case. It turns out to look like this: a plus b times t e to the r0 times t. And this is also a smooth function, no oscillations here. Finally, we have the case, what if your characteristic equation has two complex roots, so a real part and an imaginary part? We saw that you can write your equation like this, a solution: e to the alpha times t cosine of beta t plus sine, with an a, constants in front, a plus b sine beta t. So here you have oscillations because you have sines and cosines in there, and you have a time-dependent amplitude. So your amplitude is the thing out front here, which depends on time. So oscillations with amplitude depending on time. So we're going to see exactly all of these situations in the physical system now. So let's move now from the math to a physics, and all of these same considerations will still be there. So finally, we can go back to our simple harmonic oscillator, the mass on the spring. Here's the figure we've seen many, many times. Spring force pointing to the left, and that causes the displacement, the acceleration of the object. And now let's make it more complicated. So let's make it more realistic. Let's add a drag force to kind of help you visualize it. You could imagine this thing being underwater, so it's in a very thick fluid, and so that at any given instant, like suppose at this instant that is shown, it's moving to the right, then the drag will slow it down. So the drag force in this case will be pointing in the opposite direction of the velocity, and always, right? So if it was moving to the left, the drag force would be pointing to the right. So now you've got an additional force on this oscillator, and we're going to talk about what happens to it. So this is what we call damping. Any real mass on a spring in the real world will eventually come to rest, and that's due to the drag force. The mass will eventually come to rest. Now, the exact motion of the mass depends on how strong the damping is. So you could imagine, it doesn't have to be water or a thick fluid. It could just be in air. If you have a mass on a spring in air, it will eventually settle down and stop moving. But think about the differences if the fluid is very, very thick and the damping is really strong versus the fluid being kind of pretty weak and not doing too much. see if you can visualize those two cases. So this first animation I'm going to play for you is the case where the damping is very weak. So the drag force is not going to do too much to the motion of this object. You can see that its oscillation is going to slowly die out eventually. It will come to rest. Now imagine this mass is in some really, really thick fluid, so kind of like molasses or syrup, and you pull it, and notice you don't see the oscillations. It just comes directly back to equilibrium. So we have, if the damping is weak and the damping is strong, we have completely different behavior of the system. So now let's try to put equations with this. Okay, so let's think about the forces acting on this object. We've got the spring force, which is minus kx, and we've got a drag force, which we write minus b times the velocity. So the minus sign tells you that it's in the opposite direction of the velocity. The drag force always slows down the object. And there's a constant here, b, which tells you just how strong this drag force is. So now let's write down Newton's second law. Sum of the forces is equal to ma. I've got two forces. I've got spring force plus the drag force is equal to ma. And I'm going to have minus kx minus bv is equal to ma, which is x double dot. And I can put this all on one side, mx double dot plus b x dot, velocity is x dot, plus kx equals to 0. That's a second order linear homogeneous ODE with constant coefficients. So we can use the same techniques we've been talking about to solve this equation. Before I go on, people usually make a simplification here. They divide both sides by m. So I get x double dot plus b over m, x dot plus k over m, x is equal to 0. And then previously we've been calling this thing omega 0 squared. And this thing, b over m, is typically called gamma. So that's just a definition. So we end up with our equation for the damped harmonic oscillator, damped simple harmonic oscillator. X double dot plus gamma x dot plus omega 0 squared x is equal to 0. And I can control the different parameters, gamma and omega 0, by changing the spring constant k. So if I change the spring constant k, that's going to affect omega 0 squared. I can change the damping, so depending on how thick the fluid is, that makes b bigger or smaller, and that will affect the damping. Or I can change m, and m affects both the gamma and omega 0. All right, so now we just have to think about solving this equation. Okay, so let's solve it. Usual techniques. Guess x of t is e to the rt. Plug into the ODE. We get the characteristic equation right there. And then, now let's solve it. So quadratic equation. R is equal to minus gamma plus or minus square root. B squared is gamma squared minus 4ac, so 4 omega 0 squared, all over 2. So I have two solutions, R1 and R2, right? One with the plus sign and one with the minus sign. So that was straightforward. We just were able to write down those solutions. But now thinking physically about what's going on is going to take a little more time. So notice I've got a square root in this solution. And so sometimes I will have the square root of a positive number, sometimes I'll have the square root of a negative number, sometimes I'll have the square root will be 0. And depending on which case I have, the mass will be doing completely different things. So just as a warm-up to kind of get you thinking along those lines, let's think physically about what's going to go on for particular cases here. So here's a simple concept test on the formula that we just derived. So notice that there's that square root there. So let's think about this particular case. So if gamma squared is much larger, or not much larger, but just larger than 4 omega 0 squared, what is going to happen to the mass on the spring? Is it going to be oscillating? Is the solution going to be in terms of sines and cosines? Or is it not going to be oscillating? And if you're having trouble thinking about it mathematically, just think about the hint. If gamma is large means what physically? So what am I doing to the physical system in order to make gamma very large? So think about it, pause the video, see if you can determine what the answer should be before going on.